Thanks very much indeed. And also thank you to Nomura Code for inviting us to attend here and to Clean Tech Investor. I want to just probably introduce us a little bit more technically. Also thank you to the Carbon Trust for doing the initial intro. But maybe a quick overview about the company background. The company was formed in 2004, and I actually had the fortune of meeting Andrew Creeth, who's one of the founders, before he set up. And I have to say, when he told me what he was trying to do, I thought he was absolutely stark raving bonkers, and he'd never get the fuel cell system to work. But I'm quite happy to say he's proved me quite wrong. And not only that, we've had some very good support from a range of both institutional and VC investors. Here are some of them. And most recently, we've just completed another funding round, which means we've raised nearly £15 million since we started in 2004. And the Carbon Trust has been a very strong supporter of us during all of that time. Just quickly moving on, in terms of who we are as well from a people point of view, we've got a very good senior executive team. There's myself and Andrew, who's the founder and the CTO. We've also got Bob Longman, who's a very experienced engineer. He's got a really good background in bringing new technologies into the market. We've also got some great advice from a guy called Matt Frank, who's used to be the head of the GM fuel cell activities over in the US. And of course, we've got our Chief Financial Officer, Joanna Dunn, who's in the audience here, who makes sure that we don't spend the money too quickly and that we get returns from that. But more importantly, we've also got a very good board of non-exec directors that have provided some really good sound advice and direction as to where to take the company. And Bob Pettigrew's here today, and also some of the other people who've got very good experience from a variety of industrial backgrounds. So, quickly onto fuel cells. Well, I think we've had all that earlier today, that this is here and now technology, and fuel cells have had lots of false dawns, but I really believe this is now the start of something quite big. In terms of fuel cell vehicles, again, lots of people have presented that. This is our main market focus. The technology we're developing is targeted at the auto market, and we have to meet all the targets and challenges that the auto OEMs have out there in terms of power density, cost, reliability, volumetric density, and everything else. And not only that, be able to utilize supply chains and technologies that they've already developed as well. The key thing for us is that the auto fuel cell market is reliant upon the hydrogen infrastructure. Again, that's been talked about earlier today. And I just want to dwell on this schematic of the fuel cell. What's different about the technology ACAL Energy has developed is that we don't use air. And that's a pretty fundamental difference from just about any other fuel cell technology that's around at the moment. What we use instead is a liquid that is able to deliver the oxygen to the membrane. And because of that, it's the liquid which actually acts as the catalyst, and we don't need to have any platinum on the cathode side of the fuel cell. And that's quite important because that's actually where the majority of the platinum in the fuel cell is. It's on the cathode. On the other side, on the anode, what's been very helpful is we don't have to do anything to that. So we can use existing MEAs and platinum-coated MEAs that have been developed for existing PEM fuel cells. We just have the platinum on the other side taken off, and then we put our normal bipolar plates around it. So in terms of a system, we've got a lot of patents around here to cover some of the technology, not just the chemistry of how we get the liquid to work, but also about the systems. What we've got is very similar to the way nature delivers oxygen to living entities. So what we have is air coming into a blower at the bottom, and that is then bubbled into a liquid, which we call the regenerator. So it's just like you're breathing in your lungs, and the oxygen from the air then goes into your blood. So our liquid's like the blood. That then gets pumped to the fuel cell, just like the heart pumps the blood to the muscles. And then in the fuel cell, The oxygen in the liquid is then reacted, and you then form electricity and heat and water. Whereas in the body, of course, you form energy for the muscles to operate, CO2 and water. So it's a very simple system. And because nature's spent several billion years developing an effective way of delivering oxygen to give energy, we believe this one might be quite efficient as well. But in terms of what we do from a system point of view and a cost point of view, it's quite radical, because what we've got now is a very different way of managing the fuel cell. So in terms of the platinum and the cost benefits of that, that's fairly obvious. If you don't need any of the platinum on the cathode side, you can reduce that by quite a lot. Also, we don't need to use any cooling. And the reason we don't need to use any cooling is the fact that the liquid is an aqueous-based liquid. And that means that we don't need to have cooling plates, because the liquid acts as the coolant. Also, because of that, we don't need to have any water management, because the liquid takes the water away from the reaction as well. And we don't need to worry about humidification of the air coming in, because it's already in solution. And we don't need to worry too much about air management, because we're just pumping liquid around. So you can see that we end up having not only a cost down in terms of how the cell is made, but from a system perspective, we also have significant cost down as well. So what is that liquid we've got? Well, to try and not go into too much technical detail and also get out of my comfort zone myself, it's basically a self-assembling inorganic molecule. And it's based on a polyoxometallate compound. Now, in layman's terms, what that means is that in the middle of this rather complex structure, as you can see a schematic of the molecule we use there. In the middle of that, we have a metal. Now, in the blood, that's iron. In our case, it's a vanadium or a molybdenum complex. But what it means is that because this is a very thermodynamically stable setup, is that if that structure is kind of like damaged, it will self-assemble and reform into that structure again, which means we have a lot of inbuilt durability and ruggedness put into our system. And it means that we don't have to worry about the catalyst being destroyed during operation. And we've got quite a lot of data to support that that is the case, that the catalyst in the liquid, the complex, does not denature over time. The other thing that makes this quite interesting as well is that if you look at it from a chemistry point of view, it's not a pure fuel cell. The hydrogen side is a fuel cell, but the cathode, the oxygen side, is the same as a reflow battery. So we've got like half a reflow battery and half a fuel cell. And that could give us some other benefits from a system perspective. So what have we got? It's all very well and good talking about novel technologies. So what does that mean when you actually put it into the cell, and how does it work? Well, we are currently undertaking long-term durability tests. We're using a test protocol from the automotive industry, and the graph at the bottom on the right there shows that that test range. What we've got along the bottom is 0 to 2,500 seconds, which, to help you out, is about 35 minutes. And what it is, it's to simulate a typical urban driving cycle. So as you can see, somebody gets in the car, gets out the drive, gets stuck in traffic, start, stop, start, stop, start, stop. Then they go along on an urban freeway, come to a roundabout, stop, go to some traffic lights, stop. And then finally, at the end, they're at wherever they're meant to be. They turn the engine off, and there's a purge. This is a very difficult cycle for fuel cells. It's deliberately designed to enhance any decay mechanisms that are present in there. So it's designed as a destructive test to see how good the fuel cell is. And as you can see there, this is our data, and it's going out to 3,000 hours. And actually, we don't see any degradation. And as of last night, it was at 4,876 hours, and it was still flatlining. And more importantly, it had already gone through nearly 8,000 purge cycles. And a purge cycle is where, when you turn the fuel cell off in an auto, to make sure that everything is in a stable state, you then have to pump air through it to flush out all the hydrogen and any surplus water that's in there. that actually puts stress on the membrane and is a known decay mechanism as well. So we're showing that this is a very robust system. The other thing that is very unique about it, because it's half a battery and half a fuel cell, is that we get instantaneous response to change in load. And we can go from 0 to full power in less than a second in any running environment. Now that's really important, because actually in a car, to get a fuel cell in a car to go from 0 to 100%, you've got to ramp up the airflow in there, you've got to get the compressors engaged, and you generally have a couple of seconds. It's like a turbo lag. But this is actually instantaneous power. And to get away from that in the auto industry, they use a lot of batteries and supercaps to try and smooth out and give you that instant acceleration. So we could have benefits there. In terms of how we perform against standard fuel cells, this graph just shows the red line there is the performance as stated by Gore, who are a membrane supplier to the industry. This is a typical one for their stationary power. And as you can see, in July, we'd managed to achieve better than industry standard. And our developments since then, at the beginning of this month, we're now showing significant improvement on that. And by the end of this year, we expect to be able to demonstrate greater than auto required performance. So that's been able to achieve in excess of the 0.9 volts, or getting close to 1 volt at the open circuit voltage. In terms of the system, what does this really mean? Well, this is a really nice diagram showing how a typical automotive fuel cell system is laid out. And as you can see, there's quite a lot of this that is not required from an automotive application using our technology. We've got a lot of technology that means that we don't need to have all of this temperature and thermal management, which is in the left-hand corner there. That's all replaced with our regenerator technology. And in terms of all the air management and control systems and equalizers and humidifiers, they all get removed. We don't need that at all. So we can remove quite a lot of the ancillary plant required to make the system work in the automotive. And this is what we're now getting to demonstrate at a system level over the next few months. So that's what we're doing in the lab. But the most important thing for everybody in the fuel cell industry is how you're going to get into the commercialization. And one of the things that really attracted me to ACAL and was really something that convinced me they'd got something was really this. Earlier on this year, the very first system that ACAL have developed was installed at the Solvay site in Warrington. This is an industrial chemical complex that uses hydrogen to make hydrogen peroxide. And this is a system that's been installed by their peroxide plant outside. As you can see, it's just got a glass lean-to, or as the people call it, the bus shelter there, to protect it. And this was the first system that was moved out of the lab. Now, I've been involved in quite a few fuel cell companies, and there are some people here who know what I'm talking about as well. The most dangerous step a fuel cell company can make is taking its system from a lab and putting it into the real world, because the vast majority of them don't work. And work in the lab, but you can't get them to work in the real world. And it's been a big problem for a lot of new startup fuel cell companies, getting it to work in the real world. Well, this system works and has been working all the time. It was installed in the winter. It's worked all the way through the winter, all the way through the summer. In fact, the only problems we've had are the problems that you would expect in a system. We've had power electronics and we've had inverter problems. But as far as the fuel cell stack's been concerned, we've had 100% availability and it's worked first time. What this system is actually doing is just providing a backup charge to a battery system that has to ensure that the pumps are working all the time on this plant. So it's not actually safety critical, but the great thing about it was that we had to design this plant to work on a real life chemical plant, and so it's designed to be safe, and it's also been designed to be rugged as well. And I'm really, really impressed with the way that this fuel cell technology is showing how it operates in the real world. So what are we trying to do? Well, we've talked about the automotive, but one of the things that's really nice about ACAL technology is we believe that we can use the same stack architecture from automotive in stationary. Now, if we can demonstrate this in a system level, this could be a big game changer, because if you look at the stationary power market, the typical equivalence in the range that we're looking at, the 10 to 100 kilowatt range, is about $500 a kilowatt. That's typically what you pay for a diesel genset. Can be 400, can be 800, it depends what type you get, but typically about $500 a kilowatt. If we are able to deliver against the automotive targets of less than $40 a kilowatt, that puts us in a very big game-changing technology in this market. It's also true to say that one of the big problems about all of these areas is getting the right fuel source. And for us, because we believe we can get down to these cost-competitive targets at low volumes, we're only looking to get these systems installed where we've got hydrogen on the site, so we don't have to look at the complexity of fuel reforming and everything that goes with it. And in terms of the auto business, our business philosophy here is to collaborate with more than one automotive OEM. We're not going to be a tier one supplier into that industry. We want to have joint development programs and funded project work with them to a point where we can then negotiate a license and royalty payments. We will retain the rights to the liquid chemical that we make for our catholyte or flow cath, and that also gives us the ability to continually upgrade and enhance the performance of that chemical performance. So finally, where are we? Well, this is our overview of project plan. So where we are at the moment is by the end of the year, we will be able to demonstrate at a 5 kilowatt level our technology. We will then be working on a 10 kilowatt stationary system that should be operational sometime mid-year. And that is actually the basis of another significant project we're involved with. And Richard's team's been helpful there. We're with a TSP project at Swindon, where we're going to provide a 20 kilowatt system to use the hydrogen at the hydrogen refueling station to provide ancillary power at the vehicle refueling station in Swindon. We also then plan to have stationary partners and to continue building our automotive OEM portfolio so that hopefully by 2015 we can be designed into a vehicle platform. That's it.
Thanks very much, Brendan.